Molecular geometry is usually presented as a highly predictable system, governed by the mathematical rules of valence bond theory. The baseline assumption is that any central atom with a steric number of 4 regions of electron density, will undergo sp3 hybridization to reach a tetrahedral ideal of 109.5 degrees. Ammonia, or NH3, provides the quintessential classroom example used to demonstrate these sp3 behaviors. While it doesn't hit a perfect 109.5, we can easily account for the difference. The nitrogen atom's lone pair of electrons repels the 3 adjacent nitrogen-hydrogen bonds, compressing the overall structure down to the experimental value of 107.48 degrees. This model works so reliably for common elements that we often mistake this mathematical approximation for a rigid physical law. Move down one row on the periodic table from nitrogen to its heavier group 15 neighbor, phosphorus, and those rules begin to unravel. When phosphorus bonds with 3 hydrogen atoms to form phosphine, it shares the exact same steric number as ammonia. The standard model predicts a nearly identical bond angle. The experimental reality is that phosphine's bond angle is 93.5 degrees. A 14-degree collapse cannot be mathematically explained by simple lone pair repulsion. The standard sp3 hybridization model has reached its limit. To understand why the 109-degree rule breaks down, we have to look past the shape of the molecule and examine the energetic cost of building a hybrid orbital. Hybridization is an investment. The atom expends internal energy to mix its orbitals, a cost paid only for a chemical bonding payoff. This energy level diagram illustrates the orbital landscape for a period 2 element like nitrogen. The 2s and 2p orbitals are compact and sit very close to each other on the energy scale. Because the energy gap is so narrow, the nitrogen atom easily pays the cost to mix them. The resulting sp3 bonds are exceptionally strong, returning the investment by creating a highly stable molecule. Look at the landscape for a period 3 element like phosphorus. Its 3s and 3p orbitals are larger, far more diffuse, and separated by a much wider energy gap. For phosphorus, the energy cost to mix these distant orbitals is massive. The bonds it forms with small hydrogen atoms simply cannot return enough energy to cover that upfront investment. Faced with this energetic deficit, the phosphorus atom takes the path of least resistance. It skips the hybridization process entirely. When hybridization becomes a bad investment, nature stops mixing orbitals and defaults to using the pure atomic versions. Without hybridizing, phosphorus relies on its pure orthogonal key orbitals, the px, py, and pz for bonding. 3 hydrogen atoms use their spherical 1s orbitals to overlap directly with the tips of these pure p lobes. Because pure p orbitals naturally sit exactly 90 degrees apart from one another on the x, y, and z axes, the shape of the resulting molecule must follow that orientation. The phosphorus atom's lone pair does not interfere with this shape because it remains trapped inside the spherical, unhybridized 3s orbital. Chemists call this a stereochemically inactive lone pair. Held tightly near the nucleus, it lacks the directional reach to influence the geometry or actively participate in reactions. This proximity to the nucleus explains why phosphine is such a weak base compared to ammonia. Its lone pair remains effectively hidden from the outside world. The 93.5-degree angle in phosphine stands as the precise geometric signature of pure p orbital bonding. These thermodynamic observations form the basis of Drago's rule, a definitive test to predict when hybridization will fail. First, the central atom must have diffuse orbitals, meaning it must be located in period 3 or below. Second, it must belong specifically to group 15 or 16. Third, the central atom must have at least one lone pair of electrons to remain behind in an unmixed s orbital. Finally, the surrounding atoms must have a low electronegativity, specifically 2.5 or less. This final rule acts as an electronegativity barrier. When surrounded by greedy elements like fluorine, the intense pull on the electron cloud creates a significantly stronger, more stable covalent bond. This increased bonding energy finally provides the massive payoff required to fund the investment of hybridization, prompting the atom to mix its orbitals for maximum overlap. When all 4 of these conditions align, hybridization theory is officially superseded by Drago's rule. The consistency of group 15 and 16 hydrides reveals that phosphine is an integral part of a larger periodic pattern. This table tracks the group 16 hydrides. Starting at water in period 2, the bond angle is 104.5 degrees. Moving down to period 3 with hydrogen sulfide, it plummets to 92 degrees, eventually stabilizing at 90.5 degrees for hydrogen telluride. The same trend appears in group 15, dropping sharply from ammonia's 107 degrees down to phosphine's 93.5, and leveling off near 91 degrees for stibine. This consistent convergence at 90 degrees across different groups is the empirical proof of pure p orbital bonding. The periodic table does not represent a smooth gradient of behavior. It contains distinct thresholds where the mathematical models governing lighter elements no longer apply. Does the existence of Drago's rule mean that hybridization theory is wrong? In a strict physical sense, the only exact description of molecular energy we possess is the Schrödinger equation. Hybridization is just a mathematical shortcut. It is a highly effective map that works for the compact atoms of period 2. Drago's rule marks the outer boundary of that map. It identifies precisely where the approximation fails to account for the diffuse nature of larger atoms. Drago's rule teaches us that in chemistry, the most elegant model isn't always the one with the most complex math. It is the one that recognizes nature's preference for the simplest path.